Hey, welcome back to your favorite calculus class. We're going to take a look at L'Hopital's rule. It's a rule we need before we get into improper integrals. And if you remember from your first semester of calculus, anytime you run some limits and you get like 0 over 0 or infinity over infinity, these are indeterminate, right? We don't we which tells us that it does not guarantee a limit exists, if one exists, right? Or what the limit is. And so what we did in those um, situations, like here's a couple. If you throw in -1 here, notice you get 0 over 0. And so what we did is we did some algebraic approaches. We factored the numerator, and we said, well, you know what? This rational function behaves just like this linear function. It just doesn't have a hole in it. And then we plugged the -1 in, right? And we would get our solution. Or, like in the second scenario, if you get an infinity over infinity, also indeterminate. Another algebraic technique that we did is we took the largest power of the denominator, which is that x squared right there, and we divided everybody by that x squared. And then we would throw the infinity in, and that would go to 0, and that would go to 0, and we'd end up with our 3/2, right? The problem, though, is we can't always do it with this algebraic manipulation. So it's often true, when you have maybe both, like in this scenario here, we have an algebraic and a transcendental involved here. And if you notice, if you throw 0 in, see how we get e to the 0 minus 1 over 0. So we got 1 minus 1 over 0. So we got 0 over 0, right? So we're indeterminate. And so if we split it up, we would merely end up with an infinity minus an infinity, right? If you look at the graphs on those. And so we're stuck with looking at a table now as we approach, let's see, we're approaching 0 for this function, right? So if we approach it from the right, we approach it from the right, from the left, it looks like it's going to be 2, right? And you can see it on the graph as we approach it. We do this informally. We say, well, even though it's undefined there, we're getting iteratively closer and closer to that functional value of 2. So we know the limit appears to be 2. Well, there is another way, and that brings up L'Hopital's rule. That's just an introduction, kind of a reminder from your semester 1. So L'Hopital's rule says anytime I have 0 over 0, or you get infinity over infinity, plus or minus infinity over plus minus infinity, any of those scenarios that I boxed right there at the bottom as well, then this is true, which says the limit as x approaches c of a function over a g of x function is the same as the limit as x approaches c of its derivative on the top over the derivative of the bottom. And you can also repeat this, okay? So this is repeatable as well. Now, don't try and run the quotient rule. Sometimes students try to do that. That's a pretty common error. So let's look at this first scenario. If you notice with this limit here, if we throw 3 in, we obviously get 0 over 0. And so we're like, oh, we can use L'Hopital's rule. This is indeterminate in form. And so here's what we have. And so what we'll do is we'll take the derivative of the top. Derivative of x is just 1. Derivative of that constant is 0 over 2x minus 0. And so we end up with a limit as x approaches, whoops, that's 3, as x approaches 3 of 1 over 2x. And now we can throw in the 3. And it looks like our limit here is 1/6, right? As soon as we get the limit, we're okay. We don't have to repeat L'Hopital's rule. So that's to do it with L'Hopital's rule. That's what it asked us to do the first time, with L'Hopital's rule. We could also do this with algebraic techniques. I just wanted to remind you, just like we talked about in the introduction. If you go ahead and factor this rational function, see how this rational function behaves just like 1 over x plus 3. It just doesn't have a hole there at 3. But it gets iteratively close to 1/6 as you approach 3 from both sides. So again, throw the 3 in, right? So we got 1 over 3 plus 3, or 1/6. All right, let's do another one here. Part A, let's go ahead and use L'Hopital's rule. Notice here that we have the limit x goes to 0 of, let's throw it in, 1 minus cosine 0 over 4 times 0 squared. So we got 1 minus 1 over 0, so we got 0 over 0. All right, so we can apply L'Hopital's rule because we're indeterminate in form. And so we take the derivative of 1 as 0 minus derivative of the cosine is negative sine over derivative of 4x squared is 4 times 2x. And so we've got the limit as x approaches 0 of the sine of x over 8x. Well, notice if we throw in 0, sine of 0 is 0 over 0 again. So we can use L'Hopital. We're indeterminate in form again. So we're going to go ahead and repeat L'Hopital's rule. Limit as x goes to 0. And I'm right here, I'm going to repeat this. So the derivative of the sine is the cosine. Derivative of 8x is just 8. And notice now when we throw it in, cosine of 0 over 8, we know the cosine of 0 is 1. And so this just ends up being 1/8 on this thing. And we can go ahead and do that. We can do this with algebraic techniques as well. If you remember, with this, we would go ahead and we would just multiply by the conjugate of that numerator there, so 1 plus cosine x. And so we would end up with a limit as x goes to 0 of 1 plus cosine minus cosine, those are gone, minus cosine squared x all over 4x squared 1 plus cosine x. Well, if you remember, 1 minus remember sine squared plus cosine squared is 1, so 1 minus cosine squared, we can replace that with sine squared. And notice if I throw 0 in, I got 0 here, and then I get 0 times 1 plus cosine 0. So we got 0 over 0. And so we're going to have to use L'Hopital's. Oh, I'm sorry. What am I doing? I'm doing this with algebraic technique. Scratch that. Scratch that. Don't want to use L'Hopital's here on this one. All right, so we're going to have to be creative with this and do it another way. So what I'm going to do is, if you remember, little special cases, the limit as x approaches 0 of sine x over x. Do you remember that as 1? Well, that's going to be helpful here, because what I'm going to do is I can split this up as sine x over x. I have another sine x over x times, and I still have that 4 and 1 plus cosine of x. And so notice here, that'll give you 1. That'll give you 1. So you got 1 times 1 times 1 over 4, 1 plus cosine of 0. And so we got 1 over 4 times 1 plus, cosine of 0 is 1. So we got 4 times 2. So we got, see how we also end up with 1/8 there. And that's how you're going to do that one algebraically. You see the superiority of L'Hopital's rule on that one. That's quite a pain in the butt, in my opinion there. So the rest of these problems are great you try it problems if you just want to pause the video and try them, but I'll run through each of these, and we're just going to work these with L'Hopital's rule. So notice on this first one here, we have 1 cubed minus 1, so we got 0 over 4 minus 7 plus 3. So we got 0 over 0, right? So we can apply L'Hopital's rule. So we go 3x squared minus 0 over 12x squared minus 7. And we can go ahead and throw that 1 in. And so we end up with 3/5 on that one. Let's do another one here. Notice if I plug in infinity, if you will, in other words, as x increases in magnitude, right? Remember the natural log of x is increasing. So this is going to infinity, and y equals x, of course, is also going to infinity. And so we end up needing to use L'Hopital's rule again. So this is indeterminate in form. So let's go ahead and apply L'Hopital's rule. Derivative of the natural log is 1 over x. And the derivative of x on the bottom there is just a 1. And so we have the limit as x approaches infinity of 1 over x. Well, as x gets increasingly large, right, 1 over a huge number, this goes to 0. So our answer just ends up being 0. So this is a situation, again, with infinity over infinity. So we use L'Hopital's rule. This next one, with this x minus 3x squared, this, if you're, again, we're letting x get increasingly large. And what happens here is you've got x minus 3x squared. And so this numerator part will go to negative infinity. And the denominator there will go to infinity. And so we're going to go ahead and use L'Hopital's rule on this. And so L'Hops, so limit as x approaches infinity. Derivative of x is 1 minus 6x all over 8x plus 9. Now notice as this goes to infinity, we've got a negative infinity over a positive infinity here. And so we're going to use, we're indeterminate in form again. So we're going to have to repeat or use L'Hopital's rule again. And so we've got the limit as x approaches infinity, derivative of 1 is 0, minus 6 over 8 plus 0. And so we've got negative 6 over 8, or negative 3/4 with L'Hopital's rule there. Let's keep going. Some other good you try it problems. If you want to pause the video, that'd be wonderful. Try these yourself first. Here, if we go ahead and plug it in, notice we got a sign of 0 over 0. So we're gonna have to use L'Hopital's again, right? We're indeterminate in form. So let's go ahead. As x approaches 0, derivative sign is cosine. Notice we got chain rule here. Derivative of 3x squared is 6x all over 5 times 1. And so we've got limit as x approaches 0 of 6x cosine of 3x squared. This is all over 5. And if we throw 0 in, notice we'll have 6 times 0 cosine of 0, which is 1 over 5. But we've got 0 over 5, which is 0. This next one here, we got 2 minus 2, so we got 0 on the top. And then we've got the natural log of 1 minus sine of pi times 2 over 2. So it looks like we've got natural log of 1 is 0 minus the sine of pi is 0. So it looks like we got 0 over 0. And so we got to use L'Hopital's again. So let's go ahead and run limit as x approaches 2. We got 1 over, derivative of the natural log is 1 over that x over 2. We do have the chain rule involved, so times a half, minus derivative of the sine is a cosine. Chain rule again, times a half. And so we've got limit as x, oops, that's a 2 right there. 1 over, so we got 1 over x over 2, so that's 2 over x times that 1/2 minus, oh, not my apologies, the chain rule on that is times pi halves right there. Pi halves cosine pi x over 2. Gosh, I keep wanting to write infinity there. All right, so now we can throw in our 2 and let's see what we get here. So we got 1/2 minus, we got pi over 2 cosine of pi times 2 over 2. And so we've got 1/2 minus pi over 2, and we got cosine of pi. Well, we know cosine of pi is -1. And so we got 1 over 1 plus pi all over 2. So it looks like we've got 2 all over 1 plus pi. And there's our limit using L'Hopital's rule on that one. All right, here we've got, let's throw the 0 in here, and it looks like we've got 0 on the top times 1 minus cosine 0, of course. And we got 0 minus sine of 0, 0. So it looks like we got 0 over 0. We're going to have to use L'Hopital's again. And so what we'll do here, see how we've got x times 1 minus cosine. So when we take the derivative of the top, we're going to have to use the product rule. So the product rule, if you remember, if you have f of x times g of x, the derivative of that is, I remember it as the derivative of the first times the second plus the first derivative of the second. That's how I always remember it. So derivative of x is just a 1, derivative of the first times the second plus the first derivative of the second. Well, derivative of 1 is 0 minus derivative of cosine is negative sine. So there's the product rule on the top. On the bottom, I got 3 times 1 minus derivative of the sine is the cosine, and derivative of 3x is 3. And so we've got limit as x goes to 0. Why did I write that? I'm sure like my infinities, apparently. We got 1 minus cosine x plus x sine x. Oh my gosh, and I just realized I got derivative of x. Oh yeah, that's 1. Okay, yeah, there we go. Derivative of x plus x sine x. So we got 1 minus cosine x plus x sine x all over 3 minus 3 cosine of 3x. Now if I throw 0 in, it looks like I've got 1 minus cosine of 0 is 1 plus 0 times sine of 0 is 0 all over 3 minus 3 cosine of 0 is 1. So it looks like I get 0 over 0. So we're gonna have to use L'Hopital's rule again. So I use, let me write over here. L'Hopital's again. All right, so derivative of 1 is just 0 minus derivative of cosine is negative sine plus, now here I've got to use the product rule. So derivative of x is 1, derivative of the first times the second plus the first derivative of the second. And now on the bottom, derivative of 3 is 0. Derivative of the cosine is negative sine. I got chain rule on that 3x times 3. And so we've got limit as x approaches 0 of sine x. Oops, come on. No, don't do that. Sorry, of sine x plus sine x. So we got 2 sine x plus x cosine x. This is all over, let's see, negative 10, I got a positive, 3 times 3, I got 9 sine of 3x. And notice if I plug 0 in, I get another 0 over 0, and so I got to use L'Hopital's again. So let's run it again. Repeated use of L'Hopital's rule. 2 stays there, derivative of sine is cosine, plus I got the product rule, derivative of x is 1, derivative first times the second, plus the first derivative of the cosine is negative sine, all over 9 stays there, derivative of sine is the cosine. We got chain rule involved, and so it looks like we've got as x goes to 0. Why do I want to keep writing infinity? My goodness. I got 2 cosine plus a cosine. I got 3 cosine minus x sine x. This is all over 27 cosine of 3x. And now let's go ahead and throw 0 in. I got 3 cosine of 0 minus 0 times the sine of 0 all over 27 cosine of 3 times 0, cosine of 0. So it looks like I got 3 minus 0 all over 27. So 3 over 27 ends up being 1/9 on this. All right, how about this one here? It looks like I got 0 times 5 to the 0 over 3 to the 0 is 1. So it looks like I got 0 over 0. Again, L'Hopital's rule applies, indeterminate in form. And so we've got derivative of the first, derivative of x is 1 times the second, plus the first derivative of, remember the derivative of a to the x is ln of a to the x, right? So here we'll have ln of 5 to the x. On the bottom we got ln of 3 to the x minus derivative of 1 is 0. And so if I take a 5 to the x out, I would have 1 plus x ln of 5, and this is all over ln of 3 to the x. And notice if I throw 0 in now, right, I have a limit as x approaches 0. So I got 5 to the 0, 1 plus 0 times ln of 5 all over ln of 3 times 3 to the 0. Well, 5 to the 0 is 1. ln of 3 times 1. And so we've got 1 times 1 is 1 over ln of 3. And so that's our solution on that one. All right, a couple more here. If I throw 0 in here, I got square root of 16, which is 4 minus 4. I got 0 over 0. So again, L'Hopital's rule will apply here. This is 4x plus 16 to the 1/2. So I got 1/2 4x plus 16. Now it's to the negative a half minus 0. Whoops, chain rule on that. Times 4. And then minus the 0 all over 1. And so this just ends up being limit as x goes to, why do I keep writing infinity? My goodness. 4 over 2 square root of 4x plus 16 all over 1. So we've got limit as x approaches 0 of 2 over square root of 4x plus 16. And now I throw the 0 in. And so I got 2 over the square root of 16. So 2 over 4 or a half on that. All right, now I've got my infinity here. Notice I got e to the 2x minus x to the cube. This grows in magnitude way quicker than that x to the cubed. And so this will end up going to infinity on that. And same thing on the bottom. So you got an infinity over infinity. And so you want to use L'Hopital's, obviously, again. And so we've got limit as x goes to infinity of the ln of e to the 2x chain rule on that, minus 3x squared over ln of e to the 2x times 2 plus 0. And so we've got limit as x goes to infinity of 2e to the 2x minus 3x squared over 2e to the 2x. Now notice, again, we're going to have infinity over infinity. So we got to use L'Hopital's again. So let's repeat L'Hopital's rule. So I'd have 2 ln of e to the 2x, chain rule 2, minus 6x over 2 ln of e to the 2x, chain rule. And so we've got limit x goes to infinity of 4e to the 2x minus 6x over 4e to the 2x. Oops, e to the 2x there. My goodness, we've got infinity over infinity again. So let's repeat L'Hopital's rule. So we got 4 ln of e to the 2x, chain rule. 4 ln of e to the 2x. And so we've got limit x approaches infinity of 8e to the 2x minus 6 over 8e to the 2x. And we've got it again, infinity over infinity. So let's do one more L'Hopital's rule on this. So we got 8 ln of e to the 2x, chain rule, minus 0 over 8 ln of e to the 2x times 2. So it looks like we've got a limit as x approaches infinity of 16e to the 2x over 16e to the 2x. Well, that's the same as the limit as x approaches infinity of 1, which is 1, right? Y equals 1 as x increases in magnitude, of course, still goes to 1. And so repeated use of that L'Hopital's rule is very helpful there. Well, thank you so much for watching. Taking notes. We'll see you next time.